Oh, I already have it.
I don't like those white chocolate ones, so they're just kind of hanging out there.
White chocolate's
Well, nobody here eats them, so.
white chocolate's mad.
Just a minute. Make sure this one's going. We're getting all settled, people. Good deal. Let's see you.
Hey, look at your chocolate chair. I feel robbed. I could be actually robbed. I could be actually robbed. That one is what. I had shopping in actually. I promise you. Except what we demand.
Okay.
You don't have to pay us anything. You don't have to pay us anything. Except I don't know what that is. No, I'm intimidated. I'm intimidated. Yeah, you don't have to pay us anything.
Hang on.
Oh my gosh.
Oh, it's got a update issue. No,
Yeah, I don't think.
that's what's wrong. Deal with it later. Yes. You may not have that. Chocolate's actually poison to dogs, so we don't want to ever.
Of course, you know. I made it up.
I do. Yeah, why would I?
Okay.
Yeah.
Are we all right, folks?
Wow.
Y'all are a little crazy.
Okay, this is going around topic and I'll tell you about it.
All right.
Okay. Oh. Yes. Yes. More. Open the door. Yeah, that's definitely laughing. That's definitely laughing. Yeah, that's the next laughing day. Yeah, the Nor openers. No, open the Nor. Or the Nor stoppers.
All right, guys, how'd we do? Did we like the lab?
Yeah.
That's a fun one.
Glue.
And more glue.
Yeah.
That is closer to the type of lab that gets done in physical science. So if you're joining us next year for physical science, there's a lot of similar stuff. There's Rube Goldberg machines, there's ramps, there's pendulums, there's bouncing things. It should be lots of fun. So if you're going to be joining us, that's the sort of thing you'll be doing. All right. So like I said, that lab is slightly off topic, but I wanted to do something more fun and hands-on because there's so many paper labs in an earth science class and I get bored with them and I know you do. All right. So if you've looked at your syllabus, you'll see that we've got like class and class, and then we start the big extension of the climate documentaries that we saw in the fall, and we're going to be seeing new ones again in the spring. We'll be seeing Al Gore actually had a sequel called An Inconvenient Sequel, Truth to Power. We're going to watch that, and then we have another. It's two of them, but they go together. It's like part one, part two, and that one's called Climate Hustle. So we're going to watch all of those and see what you guys think. Okay, be sure that you have that first lab, by the way. I think it's 1415. The one that's the climate documentaries. You're going to want to make sure you have that in your binder. Drew, did you hear Liam? Drew, did you hear? You're going to want to make sure that you have lab, I think it's 1415, accessible because there may be things that you want to refer to. All right, so let's start. Paleozoic, Mesozoic, and Cenozoic. Last time I did these, I had Lily's brother, Ethan, and he was kind of like a dinosaur geek when he was a little guy, so he was great at this stuff. Okie doke. So wait a minute. Didn't we just talk about this last week? Weren't we just talking about meteors? Or not last week, 2 weeks ago. Talking about meteors and meteorites. Did you guys see this in the news? I love this title. Corgi-sized meteor as heavy as 4 baby elephants hits Texas. I know. They're very dense. Super dense. Yep. But I thought it was particularly interesting that they referred to it as a corgi. So this is a news update on that. I wanted to show you guys in case you missed it because it was pretty cool. We also had some planetary alignment in the last couple days and all kinds of neat stuff going on. Okay, you get to play now because I'm tapping you. What's the deal? Hello. Nope. Nope.
I hate this.
It doesn't want to play.
You just want this.
Oh, wait a minute. Is it not? Hang on, I may have to push the enable. Paul, is that you?
Yeah.
Okay. Well, maybe not. What's the deal here?
They had to do it.
Hmm. Okay. What is it doing?
What's wrong?
It's not wanting to play my video.
Give me something.
Hello.
Don't ask things, Steve.
Hold on here. We can work around this if it doesn't want to play.
You have Subway skill.
No.
Hello. Maybe we can't work around it. What in the world?
Huh?
What in the world? Hello? Why aren't you playing? This makes no sense. Okay. Okay. Hold on here. I'm gonna fight with this for a minute because I don't know what its deal is. Well, I'll put it in your notes. Maybe the next one will play. I don't know why it's being that way. Sorry, that's weird. Weird. All right, let's do this one then. So these are some other meteors. These are not the one from Texas this week. Maybe not. Wow. This is ridiculous.
I ate the videos.
Yeah, I think you did. Something happened
No.
because it's not wanting to be nice here. Let's take that out of there. Hold on. This may be the issue.
I like the stare.
Wonderful.
Pretty sure about that.
Let's try it back one more time.
He's next on the chopping block.
Oh, okay. You left.
Canada. Where's Dad? He left for Canada. Okay. All right. This is ridiculous. Let's move on. Now, will this one go? Look at this. It's like it's not.
I believe.
Give me 1 second, gang. Let me make sure that we are. What is this? No. Go away. I didn't ask you to open up. Go away. Not that.
Oh, no.
It's like your hands were covered.
To be fair, they probably believe that 2 times
Are we online here?
during the building process.
Oh, okay. Okay.
Yeah, I would have worked if we did test it beforehand.
So stupid.
That's what killed us.
Even with.
That's when we started. Well, if we hadn't tested it, we probably would have survived long enough.
This is dumb. Okay, I'm getting irritated now. Because this should be doing its thing and it's being really stupid. I mean, I'm sorry, guys. Let me see if I can make it. It's just strange. I'm going to close this whole program for a second. Give it a sec. I'm just going to shut it down and reopen it because maybe that's the problem. This is dumb.
18 months.
Snowing. Load them up. Snowing. No, snow. Yes, dude, let's try him again. One more time, and then I'm just gonna skip past him because apparently he doesn't want to play. You want to play? Let's play. Oh, man. I love this. Look. Nope. This is a waste of everyone's time and it's making me mad.
Oh, you know it. Oh, you know it. Oh, we know it. You know it. Oh, we know it. Oh, you know it.
What kind of, I don't know, what's that?
It's the actual voice of the guy on the radio. Ohio.
Okay, hold on.
Abbott, Ohio. Oh, New York.
Somebody is going to watch the Zoom.
Here we go. Let's watch him here.
It's just open the door.
And this means we'll get commercials, but
Yeah.
it works. What do you mean? I use next. Okay, listen.
And shaking the ground in Mission, Texas. The American Meteor Society confirms a meteor was seen and heard across much of deep South Texas. News 5 reporter and meteorologist Jeremy Baker with more on where that chunk of rock may have landed.
First, we need to make one thing clear, the difference between a meteor and a meteorite. A meteor is a fireball in the sky that burns up in the atmosphere. A meteorite is one that actually strikes the ground. Here's another angle from another camera taken at 5:25 p.m. You see the ground shake and hear the sonic boom. As of now, the American Meteor Society says the terminal point of the fireball, or where it burned out, was about 10 miles southeast of Nuevo Laredo. As more reports come in, that location could change. They also said there's a good chance meteorites survived from this fireball and hit the ground somewhere. This is based on the boom reports and also the GLM recordings. It is usually many fragments and not a single stone. The meteor was even picked up by the GOES lightning mapper, which usually picks up light-producing objects like lightning.
And the way we check here at the Weather Service is, was there a thunderstorm nearby in the vicinity? And the answer for the night or the evening of February 16th is clearly no.
Even though it is rare to witness these events outside of meteor showers, they happen all of the time.
In Texas alone, since January, there's been more than 90 reports of different kinds of sightings.
The incident exciting enough for what the HTV store hopes is a boom in business.
Last night when it all happened, we kind of think the same, my sister and I, and we were like, hey, this would be really funny. We decided to wait until this morning to design it to make sure that nobody had to.
Authorities say if you do come
Survive the
across
meteor.
any fragments of the fireball, not to touch them, but to notify the authorities so it can be handled properly. Jeremy Baker, 10-5.
Yeah, there is any way that anyone's actually reported that to the authority.
Yeah, this is true.
What if space rock got found?
Yeah. Oh, hold on. It's okay. Here's the well, that's the other one. Hold on. Look. Here's the other one. This is the same meteor. Somebody caught it on video. Yeah, people are screaming. Yeah. That would be cool to see. Nope. Just flew through the sky. Yeah, broke up, and then there are chunks of it that were left on the ground. They have found some decent sized chunks.
A tree is pulled by a car.
Mm-hmm. The ground.
Human, yeah,
Yeah,
like what all, did it just hit?
just at the ground. And then lastly, I'll show you this one other one. Okay. Oh, come on.
With this incredible
Stop it.
$89 device.
Grizzlies, I don't care about. So, hey, somebody, listen. Somebody can remember how to spell this word. Put it in your head real quick. Chelyabinsk
Okay.
meteor. Okay. Make sure I get this right.
CHEL.
YA. There we go. Okay. This one was obviously not in the US. This one was in Russia. Here it is. And this was a couple years ago, and it was amazing. If it will load.
He's over a 2,150.
Hang on, why are we starting in the middle? I am frustrated as all heck with technology today. Okay, here we go. Come on, dude. Yes, the Science Channel guy. SciShow.
Meteor exploded in a spectacular fashion over Russia on February 15th, 2013. An extraordinary event documented on a level far greater than we had any right to expect, thanks to all those wonderful Russian dash cams. And we are still learning all sorts of fascinating stuff about what exactly happened here. Let's start with this. It was the largest known object to enter the Earth's atmosphere since the 1908 Tunguska event. That was when a small comet or meteor exploded over Siberia, leveling about 80 million trees over a 2,150 square kilometer area. And just for reference here, the original object is called a meteoroid. The explosion in the atmosphere itself is a meteor, and the material that reached the ground are meteorites. In this case, scientists now estimate that the mass of the original 19-meter wide object was between 12,000 and 13,000 metric tons, twice as large as the earliest estimates. It entered the Earth's atmosphere traveling at about 19 kilometers per second, 50 times the speed of sound, and began to break up at an altitude of between 45 and 30 kilometers. Here, it became the now familiar streaking fireball, momentarily glowing 30 times brighter than the sun and emitting enough heat and light to cause burns to some people's skin and retinas. Even the usually conservative NASA described the event as, quote, an extraordinarily large fireball. A study published in the journal Nature calculated the energy of the Chelyabinsk airburst as being the equivalent of 400 to 600 kilotons of TNT. Essentially, no one thought a meteor this size could cause this level of impact. In Chelyabinsk alone, more than 3,000 buildings were damaged. New analysis also suggests that impacts on a scale like this one may actually happen as often as every few decades instead of once every 150 years, as we previously believed. Most impacts occur over the ocean, of course, or in remote areas where there aren't an abundance of people with dashboard cameras. Like in most meteors, the majority of the Chelyabinsk space rock disintegrated during its fiery passage across the sky, almost all of it turning into gas and dust by the time it reached an altitude of 27 kilometers. Lucky for everyone, the atmosphere absorbed most of the kinetic energy from the airburst. At most, scientists believe that about 5,900 kilograms of meteorites ended up striking the Earth, nearly all in tiny pieces scattered along below the meteor's root. You've probably seen photos of the largest impact, a 650-kilogram meteorite that crashed through the ice into Lake Chebarkul. Apologize for my Russian. A team of researchers recovered this piece and found that, like 95% of all meteorites, it was a chondrite, a mix of minerals and metals that may be as much as 4.5 billion years old. Chondrites have changed very little from the asteroid they originally came from and can be identified because they've never been exposed to heat strong enough to melt the rock. In the case of the Chelyabinsk meteor, scientists now believe that due to its orbit, it may be related to another asteroid known as 86039, discovered in 1999, which has also come close to Earth. But important to note, this spectacular impact was not predicted, which makes me think we might want to make sure that all our asteroid trackers are, carrying the one and everything. But in any case, thanks to all the scientists who are working hard to make sure that we do not get hit in the face with a giant space rock. And thank you for watching this episode of SciShow. And a special Chelyabinsk thank you to all of our subscribers. If you'd like to sponsor a graphic with your name on it or get a poster signed by the whole crew, you can learn about these and other perks by going to subscribe.com. You can also find us on Facebook and Twitter. And don't forget to go to youtube.com/SciShow.
I'm gonna lose it. Stop talking. My goodness. I don't know.
Yeah.
See? So if you're interested and you look up on YouTube the Chelyabinsk meteor, there are, like you said, tons of dash cam. There's some people that were in a building and you can hear it coming and then you hear all the glass shatter. It was pretty awesome. So now we're going to talk Paleozoic era. And Paleozoic paleogeography. Ooh, paleogeography. So what am I looking for here? Ancient geographic setting of an area. Yusuf. Paleogeography. Very good. Okay, that's what we're looking for. Excellent. And no tectonic activity along the edge. Do we know what we're looking for here? Yusuf, do you know? Yes, passive margin. You got it. Okay. So this is what happens when you have no tectonic activity along the edges of these chunks. All right. So let's talk. During the Paleozoic era, we had some sea level changes in the rock record. We have shoreline deposition. What's deposition? Remember, you were going to say, Liam, no, Alex, what's deposition?
Do you mean the matter? The change in states of matter?
Mm-hmm.
That's
No, not that one. Sorry.
okay. Then it's particulates and such in
Yes.
a fluid.
Yeah. Mm-hmm. So this is like,
rock.
remember when we talked about erosion, there was weathering, erosion, deposition. So we have deposition here. And this is what puts sand and stuff along the beaches. So what are we looking for here? Water level rises, deep water deposits overlay, shallow water deposits. All right, Liam, what you got? All right, very good. That's called transgression. We're not going to be picky about most of this stuff. I'm going to show you your test review at the end of class, and you're going to find a lot of this stuff's we're not going to bother with it too much. So when water levels fall, shallow water deposits overlay deep water deposits. What you get, Piper? There you go. Regression, transgression, regression. They're things. That's all you needed to know. They exist. All right, now evaporites. when we get large amounts of gypsum and halite in Paleozoic lagoons. Does anybody know what we're looking for here?
Well, you might be able to find, are gypsum,
What?
is gypsum the one that creates desert roses?
Yes, it is. It's also what's in drywall. What do you have, Yusuf? Okay, so what we're looking for here are mineral deposits and impermeability. So what we get are these mineral deposits, particularly gypsum and halite. What's halite? Oh, y'all know halite.
Type of salt.
Halite is salt. Very good. Halite is, yeah, a type of salt. So you get halite and then you get gypsum, and then they can form a seal over areas. And then you have this like impermeable mineral deposit. And then glaciation. Now here we go. Sea levels transgressed and regressed over how many times in the late Paleozoic? A lot of sea level movement. All right, Yusuf? 50. Yep. All right. So we had a lot of oceans rising, sinking, rising, sinking, rising, sinking. Remember Al Gore with the rising and sinking oceans? You're going to see him again in a couple of weeks talking about that. So then we had mountain building in the Paleozoic. So we had paleogeography. Now we got paleo mountain building. Laurentia is going to get deformed. Poor Laurentia. This is where we're starting. Okay. The whole point of this lesson really is to show like how we got from where we were in the Paleozoic era as far as Laurentia to how we got to the composition of continents that we know now. So there's a name for this. It's Laurentia's collision with Taconic Island arc, and it caused mountain building in the northeastern US. Do we know, Chloe? There you go. So taconic orogeny. All right. So the taconic orogeny allowed for this squishing that happened along here. Now, this is central Maine, Connecticut Valley. That's kind of where it is now geographically. So Laurentia's eastern margin later collided with Baltic and Avalonia in the Silurian period, resulting in folds and faults. So basically, we have our first smush.
That's what, the Baltics and what? UK area?
Closer to like Greece and like down a little further, Mediterranean area, kind of in there.
That's Baltica, but I was thinking the UK because of Avalon.
Yeah, it's that whole, I think when we're talking about that, we're talking kind of like this whole chunk, right in here, right? I mean, it's a big space if you're traveling around it, but if you're talking about continents smashing into each other, it's not that big a spot. So that was our first big mush. And then we have this little bit here. The southeastern edge of Laurentia collided with Gondwana in the Carboniferous period. We're all still in the Paleozoic, right? Causing formation of southern continents and mountains in Arkansas and Oklahoma. Milo, were you going to say, or did you change your mind? Was somebody back there had a hand? No? Alex, you want?
Gondwana orogeny?
This one's actually called Ouachita orogeny, and this one's fun, right? What a fun name. Okay, so if you look here, you see this whole bend. See how it's got the little yellow line there? And you can see the topography. There are some mountains through here. And this is where you get like the edge of the Ozarks. And right there, it's called Ouachita Mountains. So it's the Ouachita orogeny that caused this squish that goes like squish, squish, right? It's just a lot of squishing going on, basically. So then Paleozoic mountain building, we had another one. This is continued pressure from Gondwana caused the formation of the Appalachian Mountains, ending in the formation of Pangaea. So what was this one? Anybody got it? Just Yusuf? What you got, Yusuf? Yeah, Alleghanian. Okay, so this is your Alleghanian orogeny. So Alleghanian. So right in here, they still call parts of this. There's like Allegheny County in that area. It's basically your Appalachian Mountains, and this is, you know, specifically this Allegheny area tends to be like,
For the hell am I like?
Yeah, I was gonna say West Virginia, Virginia, you know, Western Virginia, West Virginia and Western Virginia, Kentucky, right? All right, so you get this smush right here, and now we have Pangaea, which you all are familiar with, right? But we didn't always have Pangaea, right? We started with Laurentia. Now we got Pangaea. All right, so now what kind of things were alive during this period while these continents were smashing into each other? Now this part you're going to want to know, okay? So we have this Cambrian explosion, and during the Cambrian explosion, we had all kinds of life forms suddenly just up here, okay? So there's a reason, hang on, there's a reason we think that happened. What were you going to say? The what? Oh, Burgess shell. Yeah, we'll get there. Okay, so what caused all of this life suddenly? All this variety?
I think it's just more niches were discovered.
Yeah.
and they're-
So here's what we suspect. All right. Now, those of you who did biology, think back a little bit. So the Cambrian explosion is used to define the boundary between the Precambrian and the Cambrian 544 million years ago. Remember, MIA is million years ago. Before this time, life on Earth was mostly single cell, prokaryotic, and eukaryotic. Some simple colonial species present. Okay, first of all, prokaryotic means somebody? James. Yep, without a membrane-bound nucleus. That's correct. And then eukaryotic is, James? Has a membrane-bound nucleus. What are we, somebody?
Eukaryotic.
Hang on, Piper. Eukaryotic. We are eukaryotes. I'm a eukaryote. You're a eukaryote. No,
James Fat.
hush. So it says some simple colonial species present. What do we suppose that means? Colonial species. Piper.
Like found in original ones?
Kind of. We're getting there. Yusuf.
In a colony?
In a colony. That's what we're looking for. So these single cell organisms, but they are bound together in a colony. Okay. Yeah.
Like algae.
Like algae.
Or-
Exactly like algae. Yes.
Slime molds.
Slime molds. Great
Or
examples.
Like in,
Mm-hmm.
or other types of molds.
Yep. So that's what we're talking about here. So that's what we had. And then right where the Precambrian and the Cambrian mush together, we get this crazy burst of life. So what caused it? So what we believe caused it is a type of mutation, a genetic mutation called gene duplication. And it occurred to a group of cells we call homeotic genes. Okay, sometimes they call them HOX genes, okay? Homeotic genes. So what do homeotic genes do? They're active during embryonic development and determine body segment identity. So do we have homeotic genes?
I'd imagine so.
What do we think? Who thinks we do? Who thinks we don't? Yeah, you're right. We do, obviously, because we have body segments, don't we? I mean, we have limbs and stuff, right? So what happens is you start with something pretty simple like this. If you guys remember who did biology with me, we have sea urchins. There were different kinds of symmetry. Do we remember our two main types of symmetry, James? Yep. Bilateral, right? Radial and bilateral. So something that's radially symmetrical would be like a sea star or a sea urchin. You could fold it up like a snowflake on itself, but you'd be folding it into pie pieces. All the symmetry comes from the center. We are bilaterally symmetrical. If you cut us down the middle, we have 2 arms, 2 legs, half a head, right? So you start with these things with radial symmetry, which is pretty simple. And they have this genetic code. This is like just a diagram to show you. And they have labeled this here, HOX1. And then there's some green ones here, and then there's some blue ones here, and this is HOX13, is what they're calling this. Okay, so when we get to this guy, what we've had here is a mutation, because we got a color difference, and that's going to cause hemichordate. Okay, what's a chordate? Who remembers what a chordate is? James? Yes. Yep, chordate has a nerve cord, a central nerve cord. Do all chordates have a spine? Yusuf?
Yeah.
Nope. You're close, but nope. All right, Alex. No.
Fishes and lampreys are 2 examples.
Correct. Sharks, rays. Okay, so there's a whole class called chondrichthyes, right? These are our cartilaginous fish primarily. Sharks, rays, skates, lampreys. And these guys have a nerve cord, like you have a nerve cord going from their brain down their body, but they don't have bones. They don't have a spine. So a hemichordate, what do you think a hemichordate would be? What's hemi mean? There's our Greek and Latin stuff again. Hemi. Yeah. Half. Very good. So half a chordate. So what they're saying is it's not really a chordate, but it's kind of what? Getting there? Sort of like kind of becoming a chordate. Yeah. And then urochordates, the same kind of deal. Like we're getting a little more. And then cephalochordates. Okay. Cephalo means what? Cephalus. Cephalo. Come on, y'all. Yeah, what's a cephalopod? Cephalopod. Yeah, Alex.
Cephalus means brain.
Head, brain. Yep. Okay. So
Cephalopod-
if you look here, what's happening is you've got the same genes, chick, 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 and then look, oh, wait, this one doubled itself. And then you got 3 more others here. And then look, by the time we get to this more complicated thing, all these guys are now replicating. Each one of these is coding, and it's coding for a segment of the body. So if you look here, this green way over here in this little thing is going to end up being this green here. It's the same gene, but it has kind of associated itself in relationship to the others in a different way. So what you need to remember about this, if you're writing things down or just really paying attention, is that when the Precambrian and the Cambrian, when the Precambrian turns to the Cambrian, which we mark by this explosion of life, it's because of Hox or homeotic genes that were allowed for the production of segments of the body. And then that, as they duplicated themselves, it became more and more complex. So that's what we think caused it. So here's our Cambrian explosion. So we had the appearance of every major what kind of group living today? Do we know what's going to go here? We're going to guess. Drew?
I think it's reptile.
Reptile. Liam?
Marine.
Marine. James? Complex. Alex?
I was just gonna guess like kingdom.
I'm gonna go with Liam here. It's good. All right. So every complex, yes, but not quite every, because we're more complex. The beginning of complex. But yes, this is where we get our do what?
Just realized it couldn't be anything that wasn't in the water.
Yep, has to be in water. Yep, it's gonna start in the water. Life's gonna start in the water and make its way out. All right, so we have all these marine groups. See how these are marine? Remember that marine and aquatic are different because aquatic means water and marine means ocean specifically. Okay, so then we have the Ordovician extinction. Fun one. So more than how many of the groups which developed in the Cambrian explosion become extinct, likely due to glacial formation and regression, sea level drop? All right, Piper. More than half. Yep, 50%. That's a lot. Okay, but if you look, this is what we still have, right? This is what's going. This little timeline here is going to continue to build. All right, vertebrates diversify, fish appear, and tetrapods take to the land. What makes something a tetrapod? James has 4 limbs. All right, this little dude here would be like a very early tetrapod. So this would be almost an amphibian.
Yeah, I was gonna say it looks like a new skink.
Yeah, it kind of looks like a tadpole-ish thing. So we're getting there. All right, so here we coming in here. What's this say right there?
Jawless fishes.
What's the other word for jawless fish, everybody? Who knows?
Not
What now? Oh, you had a thing on it last year in biology. Starts with an A. Agnathans. Good job. That's right. Okay.
Lampreys, hagfish, and I can't remember the third one because I think they're all dead.
Lungfish. Lungfish. Yeah. That was funny. Just didn't want to play with me there. All right, so here they are. Bye, little guy. Oh.
Yeet.
Okay, then we had terrestrial plants. And these are not as affected as marine life because they're living on the land. So what kind of swamp plants did we have developing here in the Carboniferous period? Do we know? Yusuf? Conifers. Okay, they did. You're correct. Now, what did they lead to? Coal deposits. Or everywhere we've got coal now, big coal mines, coal, we burn it, we get electricity, we used it in trains, all that business. Coal is what was made from these prehistoric swamps, basically, because it's all carboniferous. And what's coal made of? Carbon. It's just straight up carbon, right? Okay, so Permian changes. Now we're in the Permian. So we have this little we're going along here. Where are we? So we've gone from Cambrian, Ordovician, Devonian we kind of skipped over, and now we're all the way up here. Pennsylvanian, we got some reptiles. Mississippian, we got some insects. Now we're here in the Permian at the tippy top. So we're getting closer and closer to today. So the Permo-Triassic extinction event. If you look, we've got Permian and Triassic. So your Permo-Triassic extinction event would occur right at that boundary. So we lost a certain percentage of marine, amphibian, and insect life forms. All right, Yusuf, give me one.
95%.
Of what? Marine? We're going for marine?
Yeah.
Yep, 95% he says, and he's right. And Liam, how about amphibians?
45.
65, you're close, other way around, almost. Okay, there we go. 65% of amphibians, and how many insects did we lose, Alex?
I'm gonna say 70.
33. They're pretty hardy little guys. They hang on when other more complicated things.
I could slap them to death.
If all of humanity dies, the cockroaches will still be here, won't they?
Wow.
All right. All right, let's see if this will nicely play, and if not, this is making me so mad. I don't know what the deal is with it.
Plague.
Look at that.
Plague to us.
It's just being so weird. Okay. No, it's making me mad. I'm pretty sure this one is the. Who knows?
No, they don't exist. They're part of simulation patients.
Ah, there it goes. Now, where's it playing? Oh, it's playing. Look.
In the previous tutorial, we paused our stored.
Keep going. Keep going. Come on, Dave. Come on, Dave.
I heard that glorious music, I'm happy.
Come on, Dave. You just may have to do him this way. He's coming.
Is this pre or post haircut?
I don't think he showed his face in the.
You ready? We love Professor Dave, don't we?
In the previous tutorial, we paused our story.
Trying to get this bigger. There we go. Sorry. Oh my gosh. Dave does not want to play. Come on, Dave.
Don't be shy.
Come on,
Don't
Dave.
play this on me. Dave did nothing wrong.
Come on, Dave.
Don't be shy. Come on.
Dave
Come
did
on.
nothing wrong.
What? Here he goes. Here he goes. Here he goes. I'm not gonna touch it. He knows a lot about the science stuff.
In the previous tutorial,
Okay, so
we paused our story.
Pay attention.
At the end of the Proterozoic eon and the Cambrian explosion. The first era of the Phanerozoic eon is the Paleozoic era, which lasted from 541 to 252 million years ago. It was a time of great change, and many new types of organisms evolved during the Paleozoic. The Burgess Shale provides a detailed look into the strange creatures of the time, like hallucigenia. Nature experimented with a wide variety of different body designs during the Cambrian, many of which went extinct. A factor that influenced the rapid radiation of animals was the lack of predators during and immediately after animals first evolved, which allowed for large populations since they were not hindered by predation. Life began in the oceans, and by the early Phanerozoic was beginning to invade the barren lands, pioneered by the first vascular plants, which were later followed by lungfish and other creatures looking for new food sources. The colonization of land by vascular plants had a large impact on the climate by absorbing CO2 from the atmosphere, which cooled the earth so much that it caused a mass extinction event. Land plants laid the foundation for brand new ecosystems as other organisms moved into forests looking for food and shelter, the most consequential being a population of lungfish that evolved leg-like fins. These new animals, amphibians, were the first vertebrates to walk on land. All vertebrates, from dinosaurs to humans, share a common ancestor with amphibians. Before long, the land was colonized by amphibians, which evolved into reptiles near the end of the Paleozoic. The main innovation that marks the evolution of amphibians to reptiles was the rise of the amniote egg. It allowed reptiles to reproduce on dry land, whereas amphibians must return to water for this part of their life cycle. The Paleozoic was a time of great mountain building along eastern North America. North America collided with three separate land masses, causing three separate orogenies, or mountain building events. The first orogeny is called the Tectonic orogeny, occurring 450 million years ago. The second is called the Akkadian orogeny at 380 million. And the third and final orogeny, called the Alleghenian orogeny, occurred 300 million years ago and was responsible for forming the Appalachian Mountains. These mountains were around the size of the Himalayas when they first formed, and have extensively eroded over the past 300 million years, leaving behind the resistant stumps of a once great mountain range. The Alleghanian orogeny concluded with the assembly of the supercontinent Pangaea at the end of the Paleozoic. An important geologic period toward the end of the Paleozoic era is called the Carboniferous period. A geologic period is a more specific classification of geologic time compared to an era. The Carboniferous period is named for the large deposits of coal that were formed during this time, deposits that span the entire globe. Coal forms when plant tissues are rapidly buried in anoxic conditions in coastal and inland swamps. Rapid burial of organic material requires rapid fluctuations in sea level, which are caused by the formation and melting of glaciers. So without Carboniferous glaciers, the Industrial Revolution may not have occurred. In summary, the Paleozoic era was a time of dramatic transformation for both the Earth and its inhabitants, so it seems only fitting that the era would go out with a bang. Let's move forward and find out precisely what happened to prompt the next era of the Phanerozoic eon.
Thanks for watching.
So he has lots of these videos where he goes through each of these. It's pretty cool. Professor Dave will love you so much. Okay, so Mesozoic era. Now we've moved from purple Paleozoic to green Mesozoic over here. Okay, now, what was our Mesozoic paleogeography? What are we starting with here? What formed at the end of the Paleozoic? Did you know? Who's got it? Who wants to say it? Alex.
Early large reptiles that would later develop into
Yeah,
dinosaurs.
but we're doing geography, paleogeography. What developed, Drew? Yep, but I'm looking for what's our landmass? What does our planet look like, Milo? Pangaea. Okay, we got Pangaea now. Finally, we have some Pangaea. All righty. So Mesozoic paleogeography. We had the breakup of something caused by heating beneath that caused cracking and spreading. Do we know what started to break up at the beginning of the Mesozoic? Bailey? Yeah, we had break up the crust in Pangaea. So we started with Pangaea and now it's breaking up. And then we had some kind of mid-ocean rifts which developed where plates began to spread and eventually became oceans. What was this, Yusuf? Seaways. Very good. All right. So then we had magma erupting from mid-ocean rifts, displacing water, causing transgression, followed by regression and arid conditions. Arid means dry. So what's this one? Do we know? Anybody? So this one is changing sea levels. That's what caused it. All right. So just know we started out with Pangaea. Okay. That's the big point here. We started out with Pangaea, and we had all these forces causing different tectonic movement. All right. So then now we have a different orogeny. And it's on the west coast, and it's due to the subduction of oceanic Farallon, I can't speak today, plate beneath Laurentia's western edge. So what would have been Laurentia has a western edge over here, and it's subducting under this North American plate. And we know what mountains these formed. What is this? What mountain are you? Yeah, we got the Rockies. What's this orogeny called? Do we know? All right, Yusuf. Yeah, Cordillera. Okay, so we had our Cordillera orogeny. All right. And in the first phase, the late Jurassic, early Cretaceous, we had slow, steeply angled subduction, and it formed, as we were seeing, Sierra Nevada, which is over here, part of the Rockies. All right. In our second phase, in the Cretaceous, it was faster subduction and less steep angle. And what do we form here? Do we know? Yusuf? No? Who knows? Anybody know? We got Rockies. All right. So we started with our Sierra Nevada and then our Rockies came in. So we've got it all basically all here together. And then our third phase, our late Cretaceous and Cenozoic, we had rapid and shallow angled subduction, vertical uplift from somewhere to somewhere. It's going to be from Mexico to Canada. So this one we get vertical uplift from here to here. We get our whole kind of North American continent up a bit, which is keeping oceans obviously on our east and our west and not in the middle. So what was alive during the Mesozoic? Well, let's look. We started with, here's where we are time-wise. So we have these photosynthetic organisms, and they were and still are the base of our marine food chain and basically responsible for all of our oxygen, or the majority of our oxygen. So these guys, phytoplankton is what they're called. So we had plant life, something evolved into something. All right, if you were in biology with me, you should recognize this and this. What's the difference between these?
One has seeds.
What is a pine tree?
It is.
Milo. It is a conifer. That's right. What are conifers classified as far as under plant life? Plantae, kingdom plantae, what? Who knows? Who remembers? Somebody likes ice cream and somebody else likes ice cream cones and somebody else likes apples. Do we remember? Do you remember, Alex?
One of the main difference is now there's seeds.
Correct. That's the big deal. You have seeds within a cone. What were these things called? These kind of early, they're sort of like conifers. Pineapple.
Fern.
Do you know? So we're getting there. So these are cycads. Do you remember cycads? Those of you who did biology with me? Cycadia, these are the guys that are like early ancestors. And then
That's fern.
who likes ice cream cones?
Me.
Who no? In the little memory thing, who likes ice cream cones? James, do you know?
6-year-old.
And she likes apples. And who likes ice cream cones?
Children.
Not Angie, but
Gymnosperm?
gymnosperms. Jim likes ice cream cones. Jim likes ice cream cones. Angie likes apples. Why do we say Angie likes apples?
Because angiosperm is.
Angiosperms are flowering plants, right? So they had fruit and seeds. So some mammals, and we have a dominant class. What was our dominant class?
Reptilia.
Wait a minute, Liam.
Reptile.
Well, it says some mammals, dominant class was reptiles. That's correct. All right. And then we have what kind of eggs develop, James? Amniote eggs or amniotic eggs. All right. This is a big deal because, whoops, didn't mean to click that. Oh, well. Amniotic eggs. Amniotic eggs have, as Professor Dave said, a way to keep your developing embryo nourished and fed. When you crack open a chicken egg, which you've probably all done, that is an amniotic egg, okay? There's a yolk in there. The yolk supplies a little baby chicken with nutrients as it grows, all good stuff. What is the major difference between, and you don't even know the question yet, amphibian eggs and reptile eggs? Yeah, let me see, Drew.
Amphibian eggs are soft
Mm-hmm.
water.
In the water, yep.
And reptile eggs are hard.
Are they hard? They're leathery and they're on land. So what does that leathery shell provide, Bailey? Right. It prevents desiccation, right? They're not going to dry out. Okay. And then when you get to birds, their eggshells are hard, right? And that means they're even less permeable to gas stuff seeping out, moisture seeping out. So then we had our dinosaurs. We had our archosaurs, which are dinosaurs and crocodilians, and they're very abundant. So dudes like this, if you could time travel back, you'd be looking at guys like this, which I don't think I want to play with. Then we had a mass extinction. Oh no. So what percent of marine and what percent of terrestrial organisms disappeared due to this mass extinction that we had? Parker. 9. 50. We lost 50% of marine. You want to give it a shot, Sky? How many terrestrial organisms did we lose in the mass extinction here? What do you think? She's going to guess 70? Close there. All right, so 50. 50. So basically what we have here is a mass extinction, and it took out half of marine life and half of terrestrial life. That's interesting. Typically, you would expect, because this was caused by a meteor, it's a meteorite that was left behind, but a meteor that, well, meteorite strike once it hits the ground. That's what caused this mass extinction, we believe. And where did it hit? James. South somewhere. Drew. Yep, that's where it hit. So if you look at the map,
Yucatan Peninsula.
yeah, Yucatan is the word, yep. You look right here. You see the Gulf of Mexico right there, this big spot? that giant hole, yeah, well, that's where everything is. It's the giant hole basically right here. That's what caused half of all life on Earth to go away.
Oh,
Boom.
that's what happened.
That's a giant meteor, boom, meteorite strikes right here, boom. That's where I have a giant hole there. That's what did it.
So when I'm hearing you said that, is that the Gulf of Mexico is a giant grave tombstone?
Well, no, because what happened was it hit there, all right? So it struck in the Yucatan Peninsula, and then we have iridium in the clay around that area. So that supports this meteorite theory. But it wasn't just the meteorite. When the meteorite hit, you saw the picture of that little meteorite that was corgi sized. Sonic boom, Earth is shaken, right? All right. Imagine one big enough to destroy half of all life on Earth. Imagine the seismic event that would occur, something that big smacked into the planet. Tsunamis, yes, and then it's going to cause all kinds of weird tectonic action, and then you get these volcanoes.
Just be glad it
Yep.
didn't strike further north.
True.
The biggest reason why I killed is because when it hit, it caused a lot of dust to go in the air, and it also caused volcanoes to go, and it blocked out the sun, and it froze.
Yes, that's exactly what happened. So what happened is you get this giant thing smacking. All dinosaurs are gone. All these guys are having themselves the heyday. Like they are living it up, right? And then we have this mass extinction event, this huge meteorite that we believe is what caused the Gulf of Mexico to form. And yes, it obviously brought tons of dust. It shook everything like crazy. That activated a bunch of volcanoes because the magma beneath them is now being forced up. You know, all of our seams that our tectonic plates are messing around. We probably had earthquakes everywhere. And then these volcanoes start exploding. And yes, enough of them went off that it blocked most of the sunlight, which of course is what's going to cause the death of a lot of organisms that depend on that light.
And there's a ticking time bomb beneath the US that can probably take out most of the northern.
What are we talking about?
America.
Huh?
Yellowstone.
Oh, Yellowstone. Yeah.
The only thing.
Yep. So I think it will play this time. I think we just have to be patient because it played last time. Maybe.
It would probably nuke Canada and.
Maybe.
It'd be gone. Everything would die.
It will play here.
I don't think you can save from the dust storm. Like that would be the killer. It would cause basically a nuclear winter.
Yeah. I don't know why it's been that way today. So here's our Professor Dave again. He's going to follow up where he left off.
We are making our way through the Phanerozoic eon, and we just learned about the first era within, the Paleozoic era. Let's pick things back up right as this era was coming to a close. Trouble was brewing in Siberia around 250 million years ago.
It's always
As
brewing in
convection
Siberia.
currents within the Earth's mantle changed. A mantle plume was forming. Mantle plumes are hot rising areas of Earth's mantle and are responsible for some of the largest volcanic eruptions. The Siberian traps erupted around 4 million cubic kilometers of lava within only 2 million years, which is comparable to the entire Mediterranean Sea being filled with lava. Not only did this volcanism spew large amounts of CO2 into the atmosphere, but the volcanoes erupted in the vicinity of large deposits of coal and carbonate rocks. The heat from the volcanoes burned these carbonaceous rocks, which released even more CO2 into the atmosphere. This huge outpouring of greenhouse gas into the atmosphere caused significant global warming, which along with other factors led to widespread ocean anoxia and acidification, causing the extinction of over 90% of all species. This was the largest mass extinction event of all time and is known as the Great Dying. Only time will tell if an event of such magnitude will be repeated. After the end Permian mass extinction, life immediately began to recover and evolution kicked into high gear, taking advantage of increased living space and reduction of predators. Thus began the Mesozoic era, which is known as the age of the dinosaurs, since they evolved and subsequently took over Earth during this time. In addition to the evolution of dinosaurs, which occurred around 240 million years ago, mammals also evolved during the Mesozoic, but around 30 million years later. This evolutionary head start helped the dinosaurs dominate the mammals throughout their existence. For a long time, dinosaurs were imagined to be enormous lumbering creatures, but recent discoveries suggest that they may have been warm-blooded, meaning they could raise their body temperature in cold weather, allowing them to be more active than any other animal at that time, at least until the evolution of mammals. The most impactful tectonic event of the Mesozoic era was the breaking apart of Pangaea, which began around 180 million years ago. The axis along which Pangaea broke apart would go on to become the Atlantic Ocean, as the crust was stretched and thinned down to below sea level due to the divergent motions of the mantle below. The Atlantic Ocean continues to widen to this day as new oceanic crust is created along its axis, where hot, upwelling mantle rock partially melts and solidifies near the surface of the ocean floor. Along the western coast of North America, which was also the western coast of Pangaea, convergent forces dominated, and a new subduction zone was created around 200 million years ago. This would begin a theme of continuing cycles of mountain building and volcanism that have also lasted until present day. This convergent plate boundary was responsible for uplifting the Rocky Mountains, which began forming around 80 million years ago. As we wrap up the Mesozoic era, some extraterrestrial trouble is on the way that will change the Earth's biosphere forever. The Mesozoic era ended with another mass extinction event, but this one was not of an earthly origin. An asteroid with a mass equivalent to about 50 million Titanics slammed into Earth near the present-day Yucatan Peninsula. The impact itself was equivalent to a 100 million megaton bomb. The thermal pulse from this impact instantly killed anything nearby, and the shock wave created hurricane-force winds extending out about 1,500 kilometers from the blast site. It was a seismic event equivalent to a magnitude 10 earthquake. Because the asteroid impacted the ocean, tsunamis 100 to 300 meters high radiated across the Atlantic, crashing along coastlines and penetrating up to 100 kilometers inland. Molten fragments of Earth were ejected into the atmosphere upon impact that, upon returning to the surface, would heat Earth's surface to hundreds of degrees Fahrenheit, devastating terrestrial plants and animals, but sparing most marine life due to the high heat capacity of water. The combination of these events obliterated life proximal to the impact site, but the real worldwide devastation would come from long-term consequences. Dust particles were blown into the atmosphere, where they remained for months. This blocked off sunlight, causing both perpetual darkness and a global winter. This several-month period of darkness would have likely killed off anything that relied on photosynthesis for energy, which would then travel down the food chain as herbivores ran out of food. However, the longest-term effect of the impact was the global warming associated with CO2 released from vaporized evaporite rocks, which precipitated from the evaporation of ocean water. These rocks were primarily composed of calcium carbonate, the source for the CO2, and calcium sulfate, which vaporized and reacted with precipitation to form sulfuric acid, which rained down upon the Earth. The released CO2 was the main long-term problem, raising Earth's temperature by around 7 degrees Celsius for a few 100,000 years. In addition, the rapid transition from impact-induced cooling to warming would have been very difficult for most types of life to deal with. As a result of the events just described, around 80% of all species went extinct, including all dinosaurs. Though the loss was great, events at the end of the Cretaceous period opened the door for a renewal of life and a mammal-dominated world in the Cenozoic era. Let's move forward and wrap up our journey with this third and final era.
Thanks, Dave.
Yeah, bye, Dave. Catch you later. So Cenozoic, that's where he's leaving us. We love our Professor Dave. Oh, no. We love our Professor Dave. He's so cool. So now we're in the Cenozoic era. So what era are we in right now?
Cenozoic.
Cenozoic era. We've made it. Hooray. All right. What's our paleogeography? Well, pretty much what we're used to seeing. We have a cooling, shh, Alex, we have a cooling trend. Global cooling occurred after something split from something. What was it? After Australia breaks off from Antarctica. That's about the last big break. And then we had what kind of warming? Antarctic's ice cap begins to melt. Caitlin.
Global.
Yeah, we have some, it's called Miocene in that period, but yes, it's global. And so you get so yes, you get these ice caps beginning to melt, and of course that means the sea level is going to go up. But here's the thing: they started to melt, then they stopped, then they freeze, then they're warming up again. It's all of this instability because we had cooling because the sun's blocked out. We got warming because the asteroid or meteorite or whatever it was that hit is releasing all kinds of hot gas and melting rocks. And then we have something in various stages at least a third of Earth's surface. Left deposits of clay, gravel, shape the land. What are we looking for here? Anybody? I still need a Lily and a Jack. And I got a Parker, he's hiding. Tell me, Alex.
Glaciers.
Ice ages, close, there you go, pretty close. Then we have these ice ages. All right, so we went from cold to hot to cold, cold to hot. Everything's crazy, right? It's really hard for life, right, to continue. Only the most durable and most adaptable are going to make it through. So then we have subduction in the west, which formed a particular fault, and volcanoes in the Cascade Range that is still active today. All right, Lily, what fault do we have running through California? You know it. No, what fault? Yes, we do have wildfires. That's correct. We have a big, wait a minute, let her answer. We have a big fault running through California and up into the Cascade Mountains. We talked about, we did a whole lab on it. You did land and pieces that moved. What's that big fault? Do you remember?
It's also a famous GTA map.
Yeah, it's a GTA map. I think it was a movie with, was it The Rock in that movie? Who was in that movie?
He was also, there's
Yeah.
a movie. There's also a video game series.
Give it. San Andreas is what we're looking for. There you go. Okay. So then we had an area of nearly parallel mountain ranges in the southwest of the US that was formed by stress that pulled Earth's crust apart. Do we know? So this is our basin and range province. So this is what runs along kind of this western part of the US here. Continental collisions and our final breakup of Jack, our final breakup of
Crust.
Boo. This guy, hello. Here's the word. Here's the word.
Ooh, I know.
Yeah, Jack. Our final breakup. Pangea. My heart goes out to Pangea. Woof, Pangea. Right? And then we get formation of European something and continuing formation of something else. Something. Liam.
Himalayas.
Yeah, seas, and then continuing. Yeah, Himalayas are down here. So our European seas, when they talk about that, it's like you're talking about Mediterranean. Remember before when you asked about like Baltic and whatnot and all that business? So you're dealing with like, right, all this stuff in here. All these guys. So your Black Sea, all this stuff. Baltic's up here by Sweden.
The Dead Sea.
Yeah, Dead Sea. You get all these seas that are formed from this final breakup collision. Bye-bye Pangea. Heart goes out to Pangea. Remember that Pangea's final breakup was at the beginning of our current era, Cenozoic. Okay? Then you bring. So what kind of life do we have? We have Ice Age mammals, woolly mammoths, aha, and our saber-toothed cats. And then we get Homo sapiens, humans, upright. What kind of locomotion do we have, Drew?
Did you know that when the pyramids were being constructed, mammoths were still alive? Yep.
That's interesting. Do we know what kind of locomotion humans have?
Bipedal.
Bipedal, yeah. Okay, so we got our upright locomotion. And then we get migration of early humans to populate the planet. Now, this is going to get a little weird, but this is why, scientific language is always changing. Okay? So stick with me. So the current use of the term hominid can be confusing because the definition of the word changed over time. I think your book may actually have the word hominid in it, used the way we don't use it now. Isn't this fun? All right. New definitions. The most commonly used definitions currently are hominids, and that is a group consisting of all modern and extinct great apes. That is modern humans, chimpanzees, gorillas, orangutans, plus all their immediate ancestors. Those are hominids. Then we have hominins. Oh, isn't this fun? Group consisting of modern humans, extinct species, and all of their immediate ancestors, including members of the genera Homo, Australopithecus, Paranthropus, and what I always get this one wrong, Ardipithecus. I always do that wrong. Anyway, so our previous definitions used to mean hominid used to have the same meaning as hominin. And it was therefore a useful term to designate the line leading to modern humans that was used when referring to various members of our evolutionary tree. But hominid has now been assigned a broader meaning, and it refers to all the great apes and their ancestors. Hang on, put your hand down for a minute. Arm's gonna fall asleep. And this new terminology is being used in many scientific journals already, and it's only a matter of time, but possibly years, before everybody catches up. The problem for students and teachers is that a lot of texts still use the old system, and many internet sites haven't caught up. Even those more reputable scientific establishments. So students and teachers will need to be aware that hominids can mean two different things depending on how up to date your resource is. And why do we do this? Why are we making things complicated? Hominid and hominin are derived from names used in scientific classification of apes, including humans, by international convention. Certain word endings are used for specific taxons. So remember, taxonomy is how we categorize, right? How we sort. Or levels of classification. For example, family always ends in I-D-A-E. Example, hominidae. Hominidae. Subfamily names end in I-N-A-E. Homininae. And tribe, you get this like L, names ending in I-N-I. Homininae. Okay, so name changes have arisen due to the changes in the way humans, chimpanzees, gorillas, and orangutans are classified. So for example, it was once thought that apes should be divided into 3 different groups or families. And in this scheme, humans were seen to be different, so different from the other apes that we should be placed into our own distinct family, hominidae or hominids. Now, this is how we moved. Yes? I'll tell you what's on the test. You get a test. I'll show you that when we get to it. You're doing good. So migration of anatomically modern humans. Okay, keep in mind, I got some cool stuff from my sister for my birthday, by the way. And this was one of the things that she sent me. This is an old slide. I don't know if you can see through it or not. This is an old slide that would have been used in a big projector for a biology class. And it actually is termed types of ancestral man. This is from probably like the 30s, 1930s maybe. And it's showing in the middle here. I'm pretty sure that's Neanderthal. And he's not ancestral to us. Oops, it's the wrong side. He's not ancestral to us. We used to think he was. He's not. He would be a different species. So this would be like, you have your species of canine, and maybe you've got golden retrievers and dachshunds, for example. And dachshunds evolve into, I don't know, butterfly dog. I don't care, whatever. That doesn't mean that the golden retriever is an ancestor because it was part of the same group. One tree went this way, one tree went that way. So Neanderthals are not, they're in our tree, but they're not phylogenetically, we're not phylogenetically in that line. They're on a different branch, okay?
They're on gold.
Yeah, so we started out here. This is where our first evidence of humans, and we go all these different directions. And we know that over time, humans that have settled in different places and lived in different places developed through evolution different physical characteristics that made that area more survivable. So like basically people that live in Africa have more melanin, they can withstand more sun than the people who live up here in Norway and Sweden, who sometimes don't have sun all day. It's dark all day, right?
I hear that skin cancer is bad for you.
Yes, it is. All right, so this may not do, so let me. All right, so wait a minute. So we're gonna this one here, if it'll go, it'll go, it'll go. These are so fun today. Don't know why they're being stupid. Come on, come on.
Professor Dave has.
I know it, man. Here he goes again. Professor Dave tells us all this good stuff. Eh,
At this point, we have covered the Hadean, Archean, and Proterozoic eons.
blurry
And
days.
we are working our way through the Phanerozoic eon. We made it through the Paleozoic and Mesozoic eras, which brings us to the third and final era of this eon, which is called the Cenozoic era.
Hold on.
The
Wonder if it'll
Cenozoic
Buffer.
era is
buffer a second, because that is blurry. Why is it doing that?
the period in Earth's history spanning
Eh.
from 66
It's gonna be
million
blurry.
years ago to the present.
Shh, shh, shh. Alex.
The Cenozoic
Alex.
era is called the Age of Mammals due to their rapid and intense radiation, thanks to the end Cretaceous mass extinction, which killed off the dinosaurs. The early mammals were small creatures, ranging from the size of small rodents to medium-sized dogs. The first primate, Altiatlaceus, evolved around 57 million years ago in North Africa. Primates, like other mammals, experienced rapid radiation in the Cenozoic era.
Hold on. Let me see if I can get him over here without the blur.
I saw a lemur and a
Um,
tarsier.
What did it say? History
I saw a human.
history of what?
What do you say?
History of Earth Part 4 Phanerozoic. Oh, here we go. You should be able to get this. Aha.
Also see a girl on it.
Yep. Okay.
Oh, for that last part.
Here we go.
Just on dinner.
We gotta watch a Honda Pilot ad first, it appears.
Yay.
We all want a Honda Pilot, right? Not really. Really?
Pilot Trail Street, part of the Honda line of plug-in vehicles.
Hello. Goodness sakes, this is annoying. Come on.
Yeah.
No.
Determination. Y'all, Pilot Trail Street, part of the Honda line. of
Y'all.
plug-in vehicles.
Oh. Thank you, Honda. Okay. Here's where we were.
Early mammals were small creatures.
All right,
The
here you
age
go.
of mammals, due to their rapid and intense radiation, thanks to the end Cretaceous mass
It's better, right? You can see it.
which killed off the dinosaurs. The early mammals were small creatures, ranging from the size of small rodents to medium-sized dogs. The first primate, Altiatlaceus, evolved around 57 million years ago in North Africa. Primates, like other mammals, experienced rapid radiation in the Cenozoic era. Types of primates include lemurs, gorillas, chimpanzees, and humans. The first member of the human genus Homo evolved around 2.4 million years ago from Australopithecus. Homo sapiens, or humans, emerged between 200,000 and 300,000 years ago in Africa. But this fascinating story will have to be saved for the upcoming anthropology series. By the Cenozoic era, most of Earth's continents were near their current locations, except for India. The Indian continent was making a beeline toward Asia during the early Cenozoic, with collision and orogeny occurring around 50 million years ago. This event initiated uplift of the Himalayan mountains and is still occurring to this day. Additional smaller changes in geography greatly impacted the Cenozoic climate. For example, Antarctica became an isolated continent around 34 million years ago as Australia and South America broke away, moving northward. This led to the development of a cold ocean current around Antarctica, helping trap colder air over the continent. The development of the so-called circumpolar current led to global cooling and the development of the first permanent Antarctic ice sheet, marking the beginning of the modern ice age. The global cooling was caused by the development of a robust oceanic circulation, where the cold, dense water of the circumpolar current sinks down and spreads out. This led to the cooling of the lower ocean, which set the stage for more atmospheric CO2 to be stored as sediment on the ocean floor, reducing greenhouse warming. The next major change was the development of glaciers in the northern hemisphere, which existed by around 3.2 million years ago. The cause of this is still debated, but it was probably related to the closing of the Isthmus of Panama, which occurred around the same time. The Pacific and Atlantic Oceans used to be connected where Panama is today,
Alex,
which
stop.
allowed their waters to mix. Since the closing of the isthmus, the Atlantic Ocean has become much saltier, which initiated a reorganization of ocean circulation. Gulf Stream waters stopped circulating through the Arctic Ocean, instead sinking to the sea floor around Greenland and spreading out. This shut off the transport of warm water to the Arctic Ocean, causing the surrounding regions of Greenland, Canada, and Northern Europe to cool and develop permanent ice sheets. We have been living in this Northern Hemisphere ice age ever since. Within an ice age, there are periods of time called glacial periods, where glaciers expand, and interglacial periods, where glaciers retreat. Fluctuations in climate due to changes in Earth's orbit are responsible for glacial cycles. These changes in Earth's orbit, called Milankovitch cycles, include precession, or the change in the direction that Earth's North Pole points; obliquity, the change in the angle of Earth's axis; and eccentricity, the change in the ellipticity of Earth's orbit. They operate on time scales from tens to hundreds of thousands of years. We are currently in an interglacial period with the prospect of expanding glaciers in sight, at least according to the Milankovitch cycles. We are instead barreling toward a subtropical Arctic with no ice sheets due to the global warming caused by burning fossil fuels. More on glaciers later in the series. So with that, we are now roughly familiar with the timeline describing the history of the Earth. This will be useful moving forward, as we will be referencing structures that originated very far back on this timeline. So with this understood, let's move forward and start learning.
Okay, so you continue his series, he'll tell you more about the next bit. What kind of a period are we living in, according to Professor Dave?
Interglacial.
Yeah, and what does that mean for us? What is it? It's an ice age. Okay, keep that in mind, especially as we come up onto this next lab. Oh, no, that's not. We just saw you. Stop, Dave. Put it, Dave. All right, here we go. This is the one I wanted. So this is how we know how humans migrated, and I'm gonna put it right on the other.
Would you like to follow the traces of how mankind spread?
No.
No.
Stop it. But it does. I'm gonna put it right over here.
I go, everyone away.
Everybody's waiting now. All right, so here we go. This is another commercial first because it's not gonna.
Spectrum Business is the no-nonsense way for your business to stay connected. Get the fast, reliable internet speed. Get Spectrum Business Connect your calls. Cat.
Here we
Would you
go.
like to follow the traces of how mankind spread?
Listen, this is interesting here.
How hominins have been living on this land for millions of years. But it wasn't noticed until our ancestors tried to escape from Africa. Astonishingly, scientific research has
The
shown that
time ticker at the top
7.5
there.
billion people who occupy the earth today are the descendants of a woman who lived
Just wait.
200,000 years ago in Eastern Africa. Scientists call her mitochondrial Eve. Will you not follow along with me? The traces of how mankind spread by following the footsteps of the descendants of mitochondrial Eve. Mitochondrial Eve was born and lived in East Africa about 200,000 years ago. First, let's go to the place where she was born and raised through Google Earth. You can see a huge lake and a wide meadow. Lake Victoria and Serengeti Plains. You can also see Mount Kilimanjaro. The surface area of Lake Victoria is 59,947 square meters. It is a huge lake that is 38 times larger than London, 99 times larger than Seoul, 76 times larger than Singapore, and 339 times larger than Washington, D.C. The Serengeti ecosystem is a geographical region in Africa, spanning northern Tanzania. The protected area within the region includes approximately 30,000 square kilometers of land, including the Serengeti National Park and several game reserves. The name Serengeti is often said to be derived from the word Serengeti in the Maasai language, Ma, meaning endless plains. Mount Kilimanjaro is a dormant volcano in Tanzania. It has 3 volcanic cones, Kibo, Mwanzi, and Shira. It is the highest mountain in Africa and the highest single freestanding mountain in the world, 5,895 meters above sea level. Because of its shrinking glaciers and ice fields, which are projected to disappear between 2025 and 2035, it has been the subject of many scientific studies. So far, we have looked at the region where the common mother of mankind, mitochondrial Eve, may have lived. This is where her descendants lived as hunter-gatherers. It may seem peaceful, but it is also a place of fierce life. At that time, climate change caused the prey to migrate, and it is presumed that they moved along with the prey. Now you are looking at their migration routes from 150,000 to 100,000 years ago. L is mitochondrial Eve, and LX are her descendants. Letters are human mitochondrial DNA haplogroup. Arrows are migration paths. The number in the upper left corner of the screen is the estimated age. How would you have known this? We have DNA that is inherited only through females. It's called mitochondrial DNA. We can trace back this mitochondrial DNA to find out who our ancestors were. But why is mitochondrial DNA only inherited through females? Doesn't the man have it? Of course, men also have mitochondrial DNA. However, a man's mitochondrial DNA is not passed on to offspring. Let's find out why. Mitochondrial DNA is only a small portion of the DNA in a eukaryotic cell. Most of the DNA can be found in the cell nucleus and, in plants and algae, also in plastids such as chloroplasts. Sperm from a man's body goes on a long journey to find an egg used in a woman's body to obtain descendants. Among tens of thousands of sperm, only one sperm is selected and fertilization takes place. You have experienced your first victory here, so you should be proud of being born. Not all parts of the sperm enter the egg. The tail part is left and only the head couple gate is inserted and fertilized. Herein lies the secret that men's mitochondrial DNA is not inherited. Man's mitochondrial DNA resides in the tail. This principle has only recently been used in the study of human history. By 1985, data from the of 145 women of different populations and of 2 cell lines, Hela and GM 3043, derived from an African American and A. Come respectively.
I don't know what that is.
The study published on January 1st, 1987. The published conclusion was that all current humans originated from a single population from Africa, at the time dated to between 140,000 and 200,000 years ago. After this thesis, DNA was extracted from ancient human fossils and analyzed. The map used in this video was created by referring to the results of direct mapping of these research results and data from Wikipedia.
Wikipedia, such a great source.
Link in the description below to view the mapping results by year. Now, let's watch the migration path of the mitochondrial Eve descendants again. About 60 to 80,000 years ago, a renewed expansion repopulated Africa with L2 and L3 types. About 50 to 60,000 years ago, L3 type African moved to Southwest Asia. All non-Africans are today descended from either M or N types, both descended from an Africa L3 type. The group leaving Africa must have been very small, given that only 2 lineages survive. The M and N types, which left India about 600,000 years ago, arrived in Australia around 50,000 to 40,000. This was the Ice Age, and the seas near Indonesia were all land. It is called Sundaland. It is presumed that they crossed the sea by constructing a raft near present-day Bali. They were the first navigators of mankind. At this time, between New Guinea and Australia was land. Some of the M and N types that migrated to Australia between 50,000 and 40,000 years ago changed direction and head towards East Asia along the eastern coast, crossing the M and N type Eurasian grasslands that lived in Western Asia and heading to East Asia. Many races are born in Western Asia. I, U, H, V types go to Europe. At this time, Europe was inhabited by Neanderthals. Type X leaves West Asia a little later and heads for Siberia. It was a very cold ice age. I will introduce the life of our ancestors during the Ice Age through another video. The M and N types, derived from L3, served as the basis of mitochondrial DNA for today's offspring. Currently, Europeans do not have M-type mitochondrial DNA, which is unusual. Between 40,000 and 30,000 years, a group with mitochondrial DNA of type A, B, and F derived from type N appears in East Asia. At the same time, C, G, and D types appear. C and Y types also appear. They have M type as their ancestor. Type D advances to Japan via the Korean Peninsula. The last glacial maximum period begins in 33,000. LGM lasts as long as 25,600. During this time, large continental ice sheets existed in Europe and North America. The sea level was also 120 meters lower than it is today. The west coast of the Korean Peninsula and the Bering Sea were connected by land. 25,000 years ago in Asia, A, B, C, and D types spread to the east of Siberia. The X type from Western Europe also arrives here. They lived here in the coldest time. They begin to cross the Bering Sea in search of a warm place where the sun rises. It was the end of the Ice Age. It is estimated that a few types A and D crossed the Bering Sea 20,000 years ago. Around 15,000, a type arrives in Alaska in groups. This is the time when the Earth's temperature rose after the last ice age. Sea levels would rise again, but the Bering Sea would have been covered in ice. The period between 14,690 and 12,890 before was the Bowling-Allerud warming period. The Nordic Fennoscandian ice sheet begins to melt. This is the period when I, U, V, J, H, and V types began to migrate to Northern Europe. Types A, B, C, D, X, who lived in Alaska, moved to South America. Some of them arrived in South America 12,000 years ago. At that time, there was a huge continental ice sheet on the North American continent. The Laurentide ice sheet to the east and the Cordilleran ice sheet to the west coast of North America covered the continent. Now, how were they able to move south? Recent research suggests that an ice-free corridor opened between two ice sheets before 12,600. Types A, B, C, and D traveled along this route over 1,000 years, reaching Central and South America. The Earth's temperature begins to rise after the end of the Ice Age. Then, between 12,900 and 11,700, the temperature of the Earth's clouds suddenly drops. This period is called the Younger Dryas period. It was found that this was because Lake Agassiz in North America burst and flowed into Hudson Bay, affecting the thermohaline circulation system.
Yada yada. So he goes on for a while. We're running out of time. So yeah, that one didn't work. So hang on, pay attention for a minute. Okay, we've got to go. So these will be up for you, your answers. Now, you have a test coming up. Of course, I will make this sheet possible for you to see. Here's what you need to know. Geologic timeline, cross-cutting relationships, stratigraphy, superposition, lateral, non-lateral unconformities, relative absolute dating, radiometric dating, isotopic decay, types of fossilization, meteors, meteorites, and their role in age dating, temperature changes in Earth's history, evolution of Earth's atmosphere, end of Pangea, Cambrian explosion, genetic theories, Homo sapiens and migration, and understand how to compare and contrast. I've had these questions in your homework. Compare and contrast, and I get one thing. They're different cuz. They're alike cuz. No, compare and contrast requires two-part answer. You compare, you tell me how A and B are alike. You contrast, you tell me how A and B are different. There's going to be compare and contrast on this test. If you give me compare and not contrast, or contrast and not compare, I can't give you full credit. Got it? Got it. Come get your coins, kiddos. Spin it around. Hang on. There you go. Professor Dave is the best man. Oh, thank you. Where did it end up?
Straight down.
Yeah, what's up with that? It wasn't properly caught. Oh, sweet. Well, that works. Okay, it just wasn't.
James. I don't know.
Or improperly caught.
Like sit.
Those should be.
What?
Shoot. Bounced off of him.
One.
Oh, not for you, Lamb. Oh,
This one.
We've got one.
I know, I should have got.
Parker also got one.
Ha ha ha, Bridget's. Can I have your points?
No.
Fine, here it is, I already took it.
You kind of
We both got one.
What are you
okay?
eating?
And you can't even eat.
What?
Yeah, Getting laundry this morning, they come up with one now. Get family by longer. But he'll be computer director after we'll probably say we're paid there. See you later.
boy. Yeah. Oh no. Nice dog. Oh no. I missed you. I haven't seen you all day and my fuzzy boy. It's just mom. Yeah. Okay. Oh. Good boy. I'm gonna get it. Vas-y.
Oh, you heard me. You know, ask somebody about this. Granny, that helps please.
Oh, it's
The sprinklers, I have to turn on, but that's, they are, they don't hook it up, they don't hook it up, but the sprinklers on, here, Michael? Yeah, everyone well? Did you hear it? Very super sunshine with the moving around today. So be aware that there are chemicals in the grass, because they came to get our pre-emergent stuff today. So we're trying to let the grass get water before the dogs get out there, because we said it could burn their feet and stuff otherwise.
Look at that baby boy.
You got a book?
What are you doing? Oh, you got a toy.
You got your phone? Sit, dumbbell.
It's the yellow one.
Oh, yellow bug. He had the dumbbell earlier, and he was prancing about, and then what you got? As look. Somebody's boat is still floating out there. That was very entertaining. Okay. Let me get this done here.
Ozzy, come here, boy. Hey, what are you doing?
Oh, it's still going. Come on.
Like that. What?